we have components, capacity and conductivity and resistance. Okay. And in the U analogy, that was the first one, we talked about, well, voltage corresponds to a force and the current corresponds to a velocity. And then we identified and said, okay, inductivity has something to do with the mass. Resistance is just like damping. So we have here the damper constant for damping. And capacity has something to do with elasticity. And then we have a constant, the spring constant K. And actually it's 1 over K, so a large capacitor corresponds to a small K. Okay, but last time we talked about Fi analogy, so things change around. And a current becomes a force. And then likewise the voltage now becomes the velocity. And that has also an effect on these components. They switch places. And that means now the capacity becomes a mass. And the inductivity is being of a spring constant. And I think it's a 1 over again, yeah? So, and a resistor also means we have damping, but again here it's a 1 over. Okay, here I would have to look up. And that's that thing when you have no screen there. So, let's see. Is that correct what I just said? So, K is L, that's fine, okay. Okay, and then we always talk about balance and mechanical balance. So at each object or each link, whatever, the sum of forces is 0. Forces normally act in parallel. And okay, here we have in this property then currents. So we are talking about then a node, and all the currents in or out of a node add up to 0. And well, then we can draw our equivalent circuits, or we can find new laws. For example, electrically, we know that on the capacitor we store charges, and the number of charges is capacity times the voltage. Electrically, also interesting, when charges change, then we have a current. So if we want to increase or decrease the number of charges in the capacitor, that will be a current. And that is the derivative. Okay, now these two laws we could translate and see what corresponds to them in the mechanical world. Well, Q is not here in the line, so let's leave that. But we have the capacity. Okay, capacity is a mass. And we have the voltage, and the voltage is a velocity. And now we see something, okay, this is mass times velocity. I think that's called a pulse or a moment or pulse. Is that right?
Impulse.
Impulse, okay, yeah. So then it's the impulse, but let's call it P. So the meaning of a charge, electric charge, would be an impulse. Well, and then what comes of this? We have the change of an impulse, and that is a current. A current becomes a force, and that is also a valid mechanical law. If you want to change an impulse, you need a force. Or we could also say, aha, okay, the derivative is well, mass normally does not change, so normally it's the velocity, and the derivative becomes acceleration, so then this would be Newton's law 10 times 8. At least it's correct. Okay, so it works. There is something more behind that, and it's really not always just an analogy. We all already talked about the loudspeaker and saw that here we have a real coupling. And well, that means when we have a current through this, through the loudspeaker, then the diaphragm here will act a force. So then we have a real coupling between current and force, and it's also the other way around. So when we move this diaphragm, we will be able to measure here voltage. So it's a double effect, and it has to do with the FI analogy. Ah, ja, danke schön, genau. Ich weiß nicht warum, aber das alles nur probiert, erscheint schon irgendwie HDMI zu erkennen, in jedem Sinne. Ja. Aber ich weiß jetzt nicht, wo ist das Problem. Das kann natürlich auch mein Kästchen sein, und das gleiche funktioniert.
Sonst eine Alternative an der Hörseite vielleicht? Okay, war das alles aus?
Prima, genau.
Sehr schön. Dankeschön, gerne.
Okay. Back and see that our loudspeaker here is a coupled system. Normally a loudspeaker, well, it's just a coil, a long coil around a magnet, and it should just have the property of a coil. That means inductivity and maybe an ohmic resistance. But due to the coupling, there is more, because the diaphragm has a mass, it has elasticity and also damping. And all these mechanical effects also affect electric measurable quantities. This looks more like a complicated circuit with some components here in parallel. Okay, that's our three main properties from the diaphragm. And if we have an external force, then this looks like a source, not a current source. We have then here formulas, and it's not just an analogy. So here we just said capacity corresponds to a mass. In the simulation, you could just use the same numbers if you're working in SI units. So for example, a mass of 2 kilograms becomes a capacitor of 2 farads. Not here. Here we have a real coupling constant, which you can find in the data sheet of a loudspeaker. And this is the alpha. So we would really need to use this alpha for the calculation of the correct element values. For example, the resistance in the model here is this alpha squared divided by B is the damper constant. Okay, and so on. Yeah, we can see that, we can measure that in reality. And for this, I bought again a machine which can analyze for different frequencies the impedance. So then let's see. Okay, so let's see how this will work. this one, yeah, so let's see. Okay, so we are starting at 20 hertz. That's the limit for what we can hear. Okay, and then here we are at 100 hertz, 1000 hertz, and maximum here is 5 kilohertz. So that should cover all the interesting things. And most notably, we have here a maximum. So there is a resonance, and this can only be explained by the mechanical properties. This comes from the resonance of elasticity and mass. Mainly, I said it's a coil, and we also see the property of inductivity. The impedance of an inductivity will increase with frequency, and that's what we see here. Okay, it's already a linear increase with the frequency. So this rise here, this comes from the inductivity. Then we have somewhere here a minimum, and there we can read out the value of the ohmic resistance of the wire in the loudspeaker. Okay, so, and you can even hear the excitation, yeah, sometimes, and it's the audible range. Yeah. Okay, so, it's really measurable. And we will talk a little bit more about that and external forces, because one important external force is the effect of air here. And that acts also on our loudspeaker. Okay, but we talked also a little bit more about this FI analogy. And one topic was when you use mechanical levers or cogwheels or so, you try to transform forces or moments and also angular velocities or velocities to make something easier to handle. And electrically, this corresponds then to a transformer, which you can build with two very, very large inductivities. But yeah, they are so large that in the end, they have no real influence. What they are doing is they can transform something that is attached to this transformer. So we said, if we have here on the right side any impedance, so it could be a resistor, but it could be anything else, called Z2, and I measure on the left side, what's the ratio of mostly AC voltage and AC current, I won't see anything of this transformer. It looks as if I had this Z2, but multiplied with a factor. And this factor does come from this transformer. It's the ratio of the windings. And well, if it's, let's say, factor 100, then you could get the square of this. This is factor 10,000. So you could change the value of this impedance by 10,000. So it's often used, for example, in power transmission lines. You know that we transmit it with several tens of thousands of volts or even hundreds of thousands of volts. And the reason behind that is we try to increase the impedance of everything that we see here in order to neglect the impedance of the wires. Wrong wires for the transmission lines normally would make a problem, but by increasing the impedance we have here in-house, for example, for motors, for vacuum cleaners, for lights, for everything, we increase that to a huge by a huge factor, and then the transmission line resistances can be neglected. Okay, but that's just background. Okay, then something we can also use for mechanical things is a law of the electric world. How can you get a maximum of power out of a source? A source normally is never ideal. It always has an internal resistance or impedance. And when you attach something, a load, well, then you will get a current. And when you have voltage and current, then you can transmit power. If your load is merely a short circuit, you will get a big current, but the voltage is going to zero, so you have no power. If your load is very, very large, well, then you will get a maximum of voltage, but really no current, so again, no power. Somewhere in between, there must be a maximum of power. And actually this is if the load impedance is, yeah, you could say nearly the same as the internal impedance, but if it's a complex resistance, so if it does contain capacity or inductivity, then it should be here the, how's it called? Complex conjugated is the name, yeah, value. So if your source contains something like a capacity and a resistance, then this external load should contain exactly the same resistance, but also an inductivity to compensate the capacity inside the source. Okay, it does not matter if it is a voltage source with a serial internal resistance or if it's a current source with a parallel resistance. This law is always true. And as a small example, last time we also talked about a water wheel, not just a traditional old one, yeah, water wheel could be part of an electric generator. And we said, okay, the water wheel, draw this here in the middle. It's not the sun, it's a water wheel. Is driven by water, obviously. So this is a flow of water. And we have here a certain velocity of the water. And we said, well, for the water wheel, this would mean it could be accelerated to a maximum angular velocity. And this maximum would be, omega is this velocity divided by the radius. Okay, so this is the center, and down here, this is the radius. And this is a kind of source. Yeah? You can say the river is an angular velocity source with the value v divided by r. Yeah. Then on our water wheel we have other moments. We have a load, for example, the power generator acts like a load, and that means we have a moment. And load, and this is typically proportional to omega, so this is a beta times omega. Beta is a damping constant. Okay, accelerating, I said, is this omega, okay, the omega source, but first of all, this produces also a moment, an accelerating moment, and this would be then, this would be a moment, m, and this would be also some beta. Then let's call up this is a beta load, and down here, this is a beta for the generator, or a beta 0, something like that, multiplied with this omega. Okay, and now we can draw an electric equivalent circuit. We can say we have a source. The source is velocity or angular velocity, according to our analogy, is the voltage source. So voltage source instead of voltage, I write here this omega. Then we have a resistor corresponding to this beta 0. But actually the value of R is here 1 over. And okay, B is not beta. Because beta movements, beta is for rotational movements, has some different units, but the meaning is the same. So I can also just write a 1 over beta here, or beta 0. And then we apply another resistance, that's the load, and there's this beta L. So we have a second resistor here, with the value 1 over beta L. Okay, so electrically we see here a voltage divider, and at this point we have another omega. This is the omega which the wheel really turns. And the omega here on the left side, that is the maximum possible value due to the river. So you could say it's the river velocity. So this is omega of the wheel at this point here. And if you want to transmit now a maximum of power from the river, from its force, into a load, then the value of 1 over beta L should be the same as 1 over beta 0. That's then an optimum. Is it really an optimum in everything? It's optimal in the sense that you can get the maximum of power out of your source. But let's redraw this on the left side with electrical components here. So we have the source voltage, and we have now, let's say we have 2 identical resistors, so this is the optimum case. But then, at our external resistor, we have just 1/2 of the voltage. And across the internal resistance, we have again 1/2 of the voltage. And that means, okay, we do have a power here, an external power, a load power, which is voltage squared divided by R. So we have a U by 2, don't forget that, squared and divided by R. But internally, we have the same power, and that power is lost. Normally it's just dissipated into heat or anything else, but this is lost for us. And that means the efficiency of this point here is just 50%. We lose 1/2 of the power out of our source. Might be okay. If it's a river, well then it's best to use the maximum of the power you can get out of it. But if it's just a battery or so, then power optimization might not be the best idea. So optimization means just we have a maximum of power. Not really the best case for always. Okay, so I write here. Eta is the coefficient of efficiency, so this is PL divided by the power that the source produces. This is the P0. Okay, and how much is that? The P0. Again, the same formula, voltage squared. So here is the complete U0 squared divided by the total resistance. In this case, 2R. 2R, okay. And then this ratio becomes just 50%. Okay, so in this case, if the two datas differ much, then we have not an optimal, and yeah, that's, you don't have to accept that. That's the point where we can use a transformer electrically. We would use then the transformer here and try to change the value of this beta L so that it matches the beta 0. Okay, and we can do the same in the mechanical world. And the analogy here was, for example, a pair of cogwheels. We will see that in a moment in one of the tasks of the exercise sheet. Okay, so that's one thing. Then something else, for the electric world where I never really felt a useful application, but again here in the mechanical world it can be used for something. It's called the source transform, and it says when you have a voltage source with a serial internal resistance, or just any serial resistance, you can transform it into a current source with the same but parallel resistance. It's the same behavior, let's say, with respect to the right side of these white bubbles. The right side means we connect there some more circuitry, more components, and for the rest of the components, it does not matter if you have a voltage source or a current source. Internally, it's a difference, because if you do not apply anything, you do not connect anything, then in this case, there will be no current. Okay, it's open circuit. And that means there will be no power lost. In the right case, well, there is a current source and the current can flow through the resistance. There will be a voltage, and that means we have a continuous loss here. And if this is a battery, then it will be emptied after some time. So internally, for the source itself, it's not identical. But to everything attached to this source, it does not matter if it's a voltage or current source. That's the meaning here of this transform. Okay, as to the values, if you have a voltage source, then you can calculate the corresponding current value. Well, just like Ohm's law, it's the original voltage source divided by the impedance. Okay, it doesn't always have to be a resistor. You can take any component. You don't have to take all components which are in series. So, for example, let's say we have a current source and parallel C and the R. It is possible just to take this current source and one parallel component, doesn't matter which one, for example, the capacitor. Just let's take these two, and you can form then a voltage source with the serial C. The R is then what will be connected here at the white bubbles, and then including the R and the bubbles here, there's no difference between these two circuits, as long as you calculate here the U0 correctly. In this case, you have to multiply the current with an impedance. Impedance of the capacitor is 1 over SC. S is the Laplace S. So you could replace this always with the J omega. Okay, so normally I would say, well, what the heck. But in a mechanical case, I found really a useful application for that. Okay, and then let's go to this exercise sheet and see what we can find there. So this is number 4C already. Okay, so number 1 we started already. The was here our law about impulse. And now for an application of this source transform. Let's say we have a motor block here. It's somehow fixed to the ground, but it's not a solid fixing. It is elastic and it has damping, so there are some constants given. On the motor we have a shaft, the shaft rotates, and on this shaft we find another mass, an unbalanced mass, and well, this will produce trouble. So you could now either say we have forces. A mass on this rotating shaft produces a centrifugal force. And we want to understand first the mechanical connections. And we want only to see vertical forces. So let's model the rotating unbalanced mass as a force source, which acts on the motor. And, well, one comment before that about rotational movements. The nice thing is we can use here also complex calculations, because we have 2 dimensions. And let's say, so we have here a circle and the center, and let's say this is then a radius. And if we have rotation, okay, then this arrow will rotate around, and we could say now, okay, the horizontal direction is a real direction, the vertical direction is an imaginary direction, and then we could write this r as well, just really a radius, r0, multiplied with e to the power of j omega t. Well, for time 0, we have here just e to the power of 0 is 1, so we have just a real value, so we start here. For another certain time, we might get here an angle, okay, so the argument here is an angle, and if this angle is pi by 2, 90 degrees, then we are up here. And then we have a completely imaginary part here, so it's just a vertical component, and so on. So depending on the time, this arrow now rotates around here. Well, and then we have a velocity, which is the derivative of r. And okay, the derivative of this is just multiplication with the j omega multiplied with the original r, so including the time dependence. And well, we could even add an acceleration. So we have an acceleration, and that is the second derivative, so j omega squared. J omega squared times r. J squared is a minus sign, so we could also write this is just minus omega squared multiplied with r. Okay, and now, if this dot here is a mass, then it produces a centrifugal force. So let's say this is a mass m. And there will be a force, and this force, first of all, let's talk about directions. The original r points here to the right side. We multiply this with j omega, okay, but with a j always means 90 degrees counterclockwise, and that means we have a velocity which points upwards here, okay? So this was the original direction, 90 degrees shift is, we have a velocity in this direction, and the second derivative means another shift for 90 degrees counterclockwise, and that shows inside. So acceleration goes then here in parallel to your vector, but inside. And that makes sense because the centrifugal force means we have to push this mass inside, otherwise it would just vanish somewhere else. So to stay on the circle, we need a force pointing inwards. So that's the minus sign here, or it comes from the minus sign, because this centrifugal force is mass times acceleration, and that means just minus mass times omega squared times r. So this is probably a known formula, but this is where it comes from. And you could say, okay, it's derived from complex oscillations. Okay, so that's the starting point, the starting idea here. And now, a model for vertical forces. Well, motor has mass, then the fixing has damping and elasticity. We can say we have a link, and on this link we have the mass of the motor, mass. Fixing is then this damper constant B, and we have elasticity, that's the spring, with the spring constant K. We also have this unbalanced mass. I mean, it's very small, so we could probably neglect it, but let's put it also here. It's connected to our mass, so we have this second, it's a smaller one, and let's call it mu for unbalanced mass. And we have this centrifugal force. So it's another force which acts here on the link. And if this is for vertical movements, then actually we could use a sine or cosine function. Yeah, but we could stick with amplitudes and put a complex oscillation behind that. Okay, so that's already the first point. And do we have to do something more? No, just the model, the mechanical model here. And we could, well, we have already written down the values of the force. Okay, that's fine. But another idea. We could also say this unbalanced mass is moving around. That means the position of this unbalanced mass is rotating between up, down, up, down, up, down. Always the same movement. So for this unbalanced mass, it sees a kind of velocity source. The velocity is always defined by the rotation. Okay, so that's another idea, but it's valid as well. So here we could also say instead of this model, so we have again a link. We have bigger mass of our motor, it's the same. We have the damper constant and elasticity. Okay, but here we replace this and say we have the velocity source, which sits between the fixed motor block and this unbalanced mass. So let's write it like this. It's a velocity source, and then attached to this, we have this smaller unbalanced mass. Okay, and now we could ask ourselves, is this true or is this true? Or could it be that both are true at the same time? Yeah, and this is something where we can use the source transform actually. And for that we can go into the electric models respectively. And let's do this here on another sheet somewhere. So then let's start with the lower one. Here we have just 5 parallel components, so 5 parallel forces, and that means we have a node with 5 parallel components. The force, centrifugal force, becomes a current. So this is a current source. Okay, so we have a current source, and this is F centrifugal. Then we have in parallel an unbalanced mass. Mass is a capacity. So we know that mass becomes a capacity. Grounded capacity. But that's fine, everything is grounded here. So this corresponds to mu. Then we have damping and elasticity. So damping becomes a resistor. And actually we provide a 1 over B. So the resistance value is 1 over B. And we have this spring becomes an inductivity. And the inductivity value corresponds to 1 K. And of course we have larger mass of the motor, which becomes another capacitor. Okay, and now the second model. We could derive it from the drawing, or we could say, well, let's apply this source transform. So let's take the current source with the smaller capacitor in parallel and transform this into a voltage source with a serial capacity. So this is again mu. But the question is, what is the value of this voltage source now? So we have here a U0, let's say. This corresponds to the velocity source. So velocity. Electrically, the voltage source would be current multiplied with impedance. So, this U0 would be current multiplied with an impedance, in this case impedance of a capacitor. And yeah, so we could write here, this is then F centrifugal, corresponds to our current. And the impedance is, well, for a capacity is 1 over S times, well, capacity, or I can just write mass unbalanced here. I'll just replace a capacity with this mass unbalanced. And S, well, instead of S, I write this J omega, and we can understand that better. Okay, we have a formula for this Fc. And you know this is mass minus mass times omega squared times r. Or we could write it minus omega squared is j omega in brackets squared. And then we have mass and radius r. Okay, so this is then Fc, replaces Fc, and we divide this by j omega and the mass, the same mass by the way, mu, mu. So a lot of things cancel out, 1 j omega and mu, and what's left is j omega times r. J omega times r, and that really is a velocity. It's exactly the velocity of this mass, this unbalanced mass, which rotates around the shaft. So from a real value, okay, or from the absolute value, this is correct. And now as for time shifts, when our mass is here at the horizontal position, okay, so that means is a vertical position, we are at 0. But then the velocity in vertical direction has maximum. Okay, so the change here is maximum. So if the position is 0, we have a maximum of the velocity. If the mass is up here, it moves just horizontal, then the velocity is 0, but we have a maximum of the position, of the vertical position. So obviously there is a phase shift, and this is always 1/4 of the total revolution. That's the phase shift between position and velocity, and that is the factor j. That's what we see here as the factor j. It means exactly this 1/4 of 1 revolution. So everything fits nicely together, and we can say, okay, yeah, so both ideas here are correct, and they will yield the same results. And so we can use both, and we can really then see this by source transfer. Okay, so a nice effect where we can really use this analogy. Yeah. Do you have questions for that? Somehow it's a mixture of, it's a little bit abstract, but this we derived here from just looking into it from a practical view. So there's seems to be a connection between abstract formula and then something that we can really see. Okay, then this is the first point. And now for the second, we already talked about our water wheel, and here we have some data about this water wheel. So the radius is given with a, instead of a mass, we have a moment of inertia, and a friction coefficient is needed because when the pedal of the water wheel goes into the water, and the water moves, then we have laminar friction, and that is the friction coefficient. It's a damper coefficient actually for linear movements. Okay, so we will have to calculate that somehow into rotational movements. So there's one step more that we have to do in calculation more. Now, at time 0, the wheel without any load is lowered into the water. The water has a certain speed. The wheel starts from no movement at all. And now let's draw an equivalent electrical circuit for this, and we should model the river as an omega source. So it has to do with the velocity, and velocity has to do with voltage. Okay, so then let's use here something like that. And we have let's see, we can get everything there. And again, this water wheel, we have the pedals. So one is down here in the water. And the water moves with a certain velocity. And we have, due to this, we have a moment which accelerates this water wheel. But the moment is not the complete, the moment is not B. Okay, moment any, not, we have a force. The first thing is we have a force here due to laminar friction. So this is not B times velocity, there's missing something. Because the wheel could move itself already. So what's important here for the damping is the relative movement, let's say the difference between the velocity of the river and the velocity of the pedal. The pedal might move itself already. Now let's add some indices. Let's say this is velocity of the water, and the pedal has its own velocity. So we need the difference between the two. So the velocity of water minus the velocity of the wheel itself. That's the source of laminar friction here. And we get the force multiplying it with B. Okay, a force produces also a moment on this water wheel because it has a radius. So down here, let's say, this is the radius. And for the water wheel, we get then a moment, which is F times R, or B times R, and then the round bracket. The next point is we should model this as a, we should model the river not as a velocity source, but as an angular velocity source. Doesn't make sense? Well, of course, the river will always flow in a straight line. It will not go round and round. But for a very small movement, let's say we can apply this law here, and we can say an omega is the velocity divided by r. So we could factor out another r, and then we divide the velocity of the water by r and the velocity of the wheel by r, and then in the round bracket we get omegas. And that's what we want here. So this is the omega of the water minus omega of the wheel. And now as a model we can say we have one voltage here, omega of the water, or calculated as velocity of the water divided by r, however you want. Then we have another point where we have another angular velocity, that means another voltage. Let's draw this as a dot here somewhere else. And between these 2 points we have laminar friction. In the electric model we have a resistor. And because we can say formula here. This is our complete moment. The moment now corresponds to what? Moment is somehow like a force. So the moment corresponds to a current. This would become then the omega. Instead of a mass, let's then add all the elements, we have this moment of inertia of the motor wheel, J. Elasticity is not used here, but the resistance, the 1 over B, okay, what we have here is 1 over B and the factor R squared. We see where it comes from. For rotational movements, this is what we call a beta. And now we can see the connection between straight line, damper constant B, and rotational constant beta. So it has to do with the radius of the movement, but it's not just times R, it's times R squared. So this is a beta. And then we could write it like this. So in order not to confuse it too much, let's write it 1 over R is the same as a beta. And this here is our B multiplied with R squared. Okay, then we said here we have another voltage corresponding to omega of the water wheel, and this has this is influenced by acceleration. We accelerate our mass, actually the moment of inertia, and that becomes a capacity. So we add here another capacitor, and this corresponds to moment of inertia J. So at the moment, this is what we have, and at time 0, you could say we have a switch, and we close the switch, and then we get this connection. At time 0, the capacitor is empty. Empty means no charge, no current, and it means we have initially no movement. And then the wheel starts rotating, it becomes accelerated. And electrically, this happens by a current which flows into the capacitor, loads it up. And well, because this is a first order system, we could even draw a step response. The step was we lower the wheel into the water, that means we switch on the velocity, and we could draw here this step response. So over time, well, what does omega do? Omega of the wheel. Okay, and we know this is this exponential curve, right? It's this typical behavior of any capacitor also. So it rises, and then there is a final value here. And the question is, what is the final value? After a long time, let's say everything is static, and that means we have no changes. Let's argue now electrically. We have no change of the voltage on the capacitor. It means after this long time we have no current through the capacitor. Has stopped. If we have no current, then also not through the resistor. Without current, we have no voltage across the resistor, which means we have the same voltage on the left and the right side. and that means the voltage of the capacitor is exactly the same as the source voltage. Mechanically, it means the water wheel will rotate with exactly the same angular velocity as the source, what the river defines. Okay, and that means we can write here, how do we call it, omega water. There's even a time constant which we can add here. So if we draw here a straight line and the initial tangent. Okay, so here is an initial slope tangent, where this tangent crosses the final value, omega water. We look on the time scale and we see here the typical constant tau. Electrically, tau would be R times C. And we can now even use the mechanical properties to calculate what the time constant would be here. R is the inverse value of 1 divided B times R squared. And the capacity becomes our J. So we have all mechanical things, and to be honest, I would have never guessed this. Yeah, my knowledge of mechanical engineering is not large enough. I would have never guessed that this is the formula, how you would get a time constant which describes how this mechanical system behaves. But it must be, because it's the equivalent of the electric circuit. And if it's an electric circuit like that, then it must be the same in the mechanical world. Okay, but that was not the question actually. We just wanted to draw here this step response. Now the second part of the question is now a load is applied, and this load is proportional to the wheel velocity. So here we have actually a beta. Okay, we have not to calculate something. Beta is given. So where could it come from? Maybe this water wheel is a generator, an electric power generator. And if you take out electric power, well, this would act like a load moment on the wheel. So we can extend our circuit and now determine static omega. That means omega after a very long time. Okay, a load is applied. So we have an additional load, which was beta times omega. When we have an additional moment, it means we have an additional current somewhere. And this somewhere is here our connection. This is our node. So here we have an additional current. It means an additional component. And because this moment is proportional to omega, or electrically, the current is proportional to the voltage, this component is a resistor. Of course, because we are talking about losses. Damping, B or beta, is always losses, and this always becomes a resistor. And so here also we can write, we have a, let's write it as 1 over RL. Load resistor is beta. So this is the new model, and now let's not draw omega over time, but let's just think what is the final value. Without the load, without the resistor, the final voltage was exactly that of the source. What is it now? After a long, long time, voltages don't change anymore. So what happens here? And a very nice simplification is always when you say you're talking about static situations, capacitor, inductivity, they're always dynamic components. So it's only interesting, let's say, if something changes then. Either the current changes or the voltage changes, but if there are no changes, you can just neglect all capacitors. You can say they are just disconnecting, the wire is disconnected, and inductivity would be a short circuit. Okay, so in this case, this capacitor does not play any role anymore after a long, long time. You can just neglect it. So what we got is we have a source voltage and two resistors. That's a voltage divider. So, and in between, the voltage here corresponds to the omega. Divided voltage is, according to our formula, source voltage, or just let's write it as omega of the water. And then the ratio of resistances. First of all, or in the numerator, we have the impedance just of our resistor, of our load resistor. And in the denominator, we have the sum of both resistors. Okay, so actually this is a 1 over beta in the numerator, 1 over beta. And in the denominator, we get the sum, so it's 1 over beta plus. And this is a bit more, 1 over b times r squared. Again, something I would never have guessed just by looking into the mechanical model, but we can apply all the electric laws, and so it must be true. Now, we can enter the values, and I will cheat now, and I will just look what is the result here. And here I see the ratio of the resistances is 0.2. Okay, so using all the numbers, this value is 0.2. Is this a position of, or is this where we can get a maximum of power out of the river? What should this factor be if we have power optimization? So what would the optimum voltage be with respect to the source voltage? What value do we have then? Sorry?
1/5.
1/2 it should be.
Yeah.
And it's we have written that on our slides. And this was the example. We have a source voltage and two identical resistors. That's the optimal case. And then across the external, the load resistor, we have 1/2 of the voltage. So that's the situation for power optimization. In this case, we do not have 1/2, it's just 1/5 in reality. And so this is not the optimum case. Okay, so what could we do to get a maximum of power? How could we change the mechanical setup? Well, that's now a job for gears. So we do not apply the load moment directly, we use a pair of gears. And we can even calculate the ratio of the number of cogs, which are optimum here, because what we want is, in the end, this value here, let's call it beta water, okay? So this value should be the same as the beta from the load. Then let's call it beta L, should be the same. At the moment it is not the same. So yeah, let's also calculate the factor here. What are the numbers? Okay, B is 0.003. The radius is 1 meter. Okay, so B multiplied with R squared is again the value 0.003. So 0.003. What we have at the moment is beta load. What's that value? 0.012. So we can correct this with a factor 1/4. So what we need is 1/4. And this value, the meaning of this value, is the ratio of the cogs squared. So this is what we call A squared, and this is the number 1 cog divided by number 2 cog squared. And if this is 4, then we can say, okay, we need 2 cog wheels where one has double the number of cogs than the other one. And by using this, we can get much more power out of our river. And well, that's why we use gears. It's also why we use gears in cars, for example, and everywhere else where we have to optimize power. Okay, so these were some, let's say, complicated examples, because it's abstract to say, we have a real situation, it's mechanics, we have to translate this into an electric world. Okay, electric circuits might be something realistic also, but this connection is somehow abstract. But you can see we can use it, and it has many applications. So, okay, we are nearly ready. I think this Thursday is again our Thursday, and then I would start with a mini project. So I would introduce you to the possible mini projects from my side, and I don't know, maybe Ben will do that tomorrow or next week, on Tuesday, show his mini projects, and the selection will be open probably end of the week or maybe starting next week. And okay, yeah, then have some nice days and see you on Thursday. Bye bye.